Good. All right, let's get started. Thank you all for coming. And thank you, Ahmed, for joining us today. Ahmed is a professor at the University of Illinois, Urbana, Champaign, and he was able to coordinate visiting with us and giving this talk with a conference he's attending up at LBL. So Ahmed got his undergraduate and master's degree at the University of Cairo in 2003 and 2005, respectively. And then he went to Caltech, where he got a master's degree in applied mechanics and a PhD in civil engineering in 2011. Then he did a postdoc at UC Santa Barbara for just a year, right? So you got to enjoy the beach there for a short time.
It's a great place.
And then joined the faculty at the University of Illinois in 2013, where he's been a professor since. And as you will see, his expertise is in fault mechanics, fracture mechanics, and even though he's in an engineering department, he's very well known in the seismology and geophysics community for the modeling work that he has done on earthquake rupture models and related topics. So thank you for coming, and the floor is yours.
Thank you so much, Roland. And I would like to make sure everybody online hears me. So if it's okay, then we can proceed. I'm really honored to be here today, and I would like to talk about this recent effort on modeling sequence of earthquakes and aseismic slip with high resolution quantum physics. And our big goal is hopefully to build up earthquake virtual machines. This work I'm going to present today was primarily done by now Dr. Mohammed Abdelmajid, who defended his thesis a couple of weeks ago and is going to Caltech as a postdoc. And then hopefully Dr. Tubi Metram and Maya, and I hope we can help him get his PhD too. I'd like to acknowledge different funding sources for it. So I'm in a civil engineering department at Illinois, and I teach earthquake engineering. And this is usually the first slide I show in the first lecture. And the objective of this slide just to show the different disciplines involved in the earthquake problem. There are physicists, mechanicists, geophysicists, and there's also seismologists, geotechnical engineers, and structural engineers. But also, I show this because of these little scatter plots that I have in this slide. And these scatter plots are meant to show the uncertainties associated with every modeling scale. And they might look identical each other, except for a very crucial difference. So at the structural scale, we do have some uncertainty, but we also have a good handle on quantifying this uncertainty and how it is going to impact these structural response. You could see that the axes are linear. We go a little bit deeper to the geotechnical layer, where we are interested in ground motion and site response. You see that I'm plotting this as a semi-log scale. So now the scatter is actually higher. And then you go more deeper and then to the source, and then like all hell break loose. And you
want a laser pointer?
And then you get a power loop, because now the scatter is kind of on a log scale. So we actually have a large uncertainty when it comes to source physics. And one might think that earthquakes happen all the time, so we have enough data to constrain this kind of uncertainty. But the truth is, we still operate in a data-limited regime. And this is like just a slide showing from USGS the earthquakes greater than magnitude 6 that happened over the last 120 years. And we can count maybe 5 big earthquakes greater than magnitude 9, maybe 50 greater than magnitude 8, and so on. So we only have a few data points when it comes to large earthquake that might not help us constrain this uncertainty. And this is why simulations are needed. And as a modeler, here's the dilemma that modelers have to deal with. in order to understand the system, the modeler must first recreate that system on the computer or a sheet of paper. Right? But in order to create the system, we actually also must have an understanding of the system. So it sounded like a vicious cycle here. Luckily, we learned how to overcome this. We need to start somewhere and then iterate. But the problem is faults and fault zones in reality are really complex entities. These are a couple of sketches for how fault zone looks like from a paper by Mitchell and Faulkner. And whether we consider the fault zone that's relatively simple with a single fault core, or one that has multiple slip surfaces, in general, fault zones have this mix of persistent localized zones within dynamically evolving structure with both discrete and distributed damage features. And this system in general is far from equilibrium and evolutionary, but luckily we have some long-lived statistical properties. And if we accept this picture, then probably the volumetric and deviatoric deformations become naturally coupled. So it's not only a slip on a single surface, but also there's some dilation and compaction associated with them. But of course, the processes would be depth dependent. And the challenge we are dealing with is that observations are limited, especially when it comes to depth, and hence, again, simulations are needed. And so our long-term goal is to build this virtual earthquake machine. And there are minimum ingredients for this earthquake machine. You need to have faults and fault zones. You need some sort of constitutive description to define the behavior of the bulk. And then you need to track stresses and frictional evolution. And most importantly, you need to put this in an evolution, a framework where you can track this feedback cycles between the different components. Of course, this builds upon early attempts, for example, to understand earthquake rupture physics through single dynamic rupture simulations. But we come to understand that these single dynamic rupture simulations, where you assume some initial distribution of stresses and frictional properties and a specific fault surface, these results that you are going to get from these single dynamic rupture simulations are critically dependent on the initial condition of the system. You may do a little bit better and say, okay, let's do an ensemble simulation where we can change the initial conditions and generate many of these rupture scenarios. But unfortunately, there is no guarantee that the earthquake system is ergodic. So whatever initial condition you might choose might not actually be within the right attractor in which the system is evolving. So the framework that we are trying to adopt is this sequence simulation, where you start with some initial condition, but let the system evolve and then start collecting statistics or describe the evolution of the system as along the trajectory it takes for evolution. But there is no free lunch here, and this problem is really highly spatially temporally complex. There are multitude of a spatial and temporal scales that we need to cover. And so I don't promise you are going to listen about the solution for all in this talk, but we focus on a specific class of problems, which turns out to be important, but also have an interesting feature. And this class of problems are characterized by the complexity is spatially localized to some extent. And to some extent, I mean, like while fault zones have geometric or material complexities, it turns out that in many cases, the most relevant ones to controlling rupture propagation tend to be relatively local. So they extend over spatial scales that are small compared to the overall dimensions of the domain you are interested in and over which waves are propagating. But they're also not very localized that you can lump them as constitutive description on the fault, like effective friction property. So there's this sweet spot where you have kind of nonlinearities and heterogeneities living between these two extremes. And as I mentioned, an example would be, for example, fault zones, where the width of the fault zone could be a couple of hundred meters, compared to a fault that extends for a couple of hundred of kilometers. And also when we do simulations, we can observe that these kinds of off-fault damage or plasticity extends on spatial scales that are very narrow compared to the length of it. However, as I will show, even if these are relatively local, they have an important impact on the rupture propagation. So for this specific class of complex problems, we developed a specific numerical scheme we call Phoebe. And Phoebe is just a combination of finite element and spectral boundary integral approach. So usually, when we have nonlinear problems, we will probably start building a finite element model. So we simulate a large enough domain and discretize it with finite element and then impose on the boundary some sort of absorbing boundary condition to let the wave come out of the system. But in Phoebe, what we do is we realize that the scale that we are interested in, the heterogeneity and nonlinearity, exists in a narrow region here. So we can just isolate this narrow region of interest in a simulation box we call a virtual domain, and discretize this box with whatever method, domain-based approach you are interested in, finite element, continuous Galerkin, whatever. But we cannot get rid of the rest of the exterior half spaces, but this is where the strain energy resides, and this is where the wave propagation happens. And hence what we do is that on the boundaries of this virtual strip, we impose the spectral boundary integral relation that connects the tractions to displacement on these boundaries. So our boundary condition for the simulation domain are now integral relations between the shear and normal tractions and the shear and the normal displacements on these boundaries. And using a spectral formulation in order to accelerate the solution of these integral relations makes it a really efficient methodology. So that's what we do spatially. But remember, we need to solve the evolution of the system over different time scales. So temporally, we have an alternating algorithm where when things are quiet and the deformation is slow, we use a quasi-dynamic formulation where we suppress inertia and just use an elliptic equilibrium formulation with time-dependent loading. And then when the rupture or the motion accelerates and waves becomes important, we switch to a fully dynamic approach where we retain the inertia effects and use an explicit time integration to evolve our system. And we switch between the quasi-dynamic and the fully dynamic based on a velocity threshold. So by combining this domain decomposition with an adaptive time stepping, we are able to bridge different spatial and temporal scales and also kind of strategically put more resources on higher resolutions in area where we really need it, where the complexity exists. And for those of you who might be interested in learning about the details and the math of this method, here are some references where we validate the technique and study its computational efficiency.
Just curiosity, can I ask one question? That the switching to the aseismic happen to only region by region could be different. Some region may be seismic, but some region may be still aseismic.
Very nice. So we look at the properties inside this box, right? And if the velocity or the slip rate everywhere becomes less than a threshold, then we understand that the inertia effects now can be neglected compared to the other terms of the problem. And so we can safely switch to aseismic.
One to the other.
One to the other. It's overall.
For the same question, does the equation the same or not?
Fantastic. So the governing equations are generally the hyperbolic equation where you have the inertia term equals to the divergence of the stress. But when you go to the aseismic phase, you can actually get rid of the inertia term and assume that you are only solving the static equilibrium equations at every time step, because the inertia effect becomes less important, and hence you assume that it's just a static problem. For that purpose, we just need to augment the fault with a term called radiation damping in order, because if the solution, if the motion accelerates towards seismic instability and we don't have this radiation damping initially, the problem can diverge. So this radiation damping just provides some kind of stabilization for the problem until we switch to a fully inertia effect combination.
Is the geometry of the fault or the cracks mesh dependent?
Well, it depends on what the problem you are modeling in. In general, we don't want the problem to be mesh dependent. I will show today things with a single fault, but a fault zone evolving around that. But you could model, we modeled before a fault with branches, you could model multiple faults, so it's not mesh dependent. But we can talk definitely about the evolution problem of faults.
And the fault is always located on the boundary between the elements here.
In this approach and in this talk today, yes, but we do have techniques that allow the fault to evolve naturally. For example, with phase field, we developed a methodology, co-developed a methodology where we can use phase field consistent with latent state friction and then allow the faults to propagate anywhere, because these phase fields are diffusive and hence can be discretized as bulk entities. Excellent question. So let me just, perhaps for the bulk of the talk today, I will just show an example of running this framework while engaging the nonlinear behavior of the bulk. And one place to start is to assume that the bulk is behaving as a viscoelastoplastic material. And the way this goes is that we introduce a yield surface with some viscous regularization here. And the yield surface basically states that the deviatoric stress has to be bounded by the yield strength with some viscous regularization, so it can actually overshoot the yield surface and then come back over a relaxation time scale. But most crucially, this fault strength is parameterized by two parameters. One is cohesion, and the other one is the angle of internal friction. That's a phenomenological description. This is called Drucker-Prager plasticity. And the crucial part here is that the fault zone strength is dependent on the mean stress. So more compression will make your rock stronger. If you have tensile perturbation, less compression will make the fault weaker. And we can definitely, and I look forward to debating whether this is the right description or not. It's not, because we actually don't know how faults or rocks evolve at this scale, but it's a plausible mechanism, and it's widely used in geotechnical engineering to describe inelastic behavior. It's a dissipative mechanism, provides energy dissipation. It can allow incorporation of volumetric changes because you could add the latency and compaction. And interestingly, it also allows you to partition the deformation if needed between the bulk and the fault, because the inelastic deformation in the bulk is like slip on the fault surface. Limitations, however, are important and cannot be neglected. There is no account for healing, at least in the classical formulation for the plasticity models. And there's no feedback mechanism on the elastic wave speed, which is an observation that people record that, okay, subsequent to earthquakes, there is a reduction in the elastic wave speeds, which actually recovers after time. So these can be incorporated through continuum damage plasticity models, and this is something we are also working on. Before just giving you examples of the results we got, I want to highlight that pressure sensitivity that I just introduced in the formulation of Drucker-Prager favors what we call directional plasticity, plastic strain accumulation. So the idea is, if you have, say, a right lateral strike slip fault like this one, on the top here, there will be increased compression just purely because of the sense of motion. So this quadrant will experience increased compression, and this quadrant, which we call the rotational quadrant, would experience reduced compression. So this part would experience compressive mean stress perturbation. This part would experience tensile mean stress perturbation. And as, of course, was shown in dynamic rupture simulations for single ruptures, if that is the case, the upper quadrant here would be stronger because it has higher compression. So it would be less prone to accumulating plasticity, whereas the lower quadrant, which experience tensile perturbations, is weaker, so it can accumulate plasticity. The results, however, there are more details and it depends on the direction of the maximum compression, which is the background tectonic stress. But this idea is the intuitive idea we think of. So let's see now what we will get in terms of the plastic strain accumulation as we crank our machine through multiple cycles. And I'm giving here just two examples. The first one is what we call a strong bulk. So we can increase the yield strength of the bulk, for example, by changing its angle of internal friction or increasing the cohesion value so it becomes strong, or reduce the cohesion or the angle of internal friction so it becomes weaker. So to start with, the first thing here, if we have a strong bulk, overall, we found a similar trend from what we get from single dynamic rupture. This is a right lateral slip, a right lateral slip, right lateral strike slip fault, ruptures nucleate somewhere here and propagate in this direction. So this is our dilatational quadrant, and this is our compression quadrant. And so in this case, what we observe is that the plastic strain has this characteristic fan-like shape, and it just accumulates where we are expecting. On the other hand, if we have a weaker bulk, say by reducing the cohesion, we observe something very interesting. We observe that plasticity, as you look at it on the long term, seems to accumulate on both sides of the fault. So it seems like the distinction between the dilatational and compressional quadrant does not exist. And before just proceeding here, we were very interested in understanding why this is happening, because there are important practical implications. People like to look at damage and, for example, infer the direction of propagation of rupture. But before proceeding and trying to explain this, I want to highlight here something that also came up in many of the discussions that I had today, which I thoroughly enjoyed. If you look at the distribution of plasticity normal to the fault, you see that it extends spatially to a really small region compared to the length of the fault. We are talking about perhaps 1% or less of the fault length having accumulating damage in the transverse direction. So it's really a localized and a narrow region, but as I mentioned, it will have an important implication. So why are we seeing this? And it turns out there are three kinds of reasons that only emerge in these kinds of sequence simulations. One, of course, is rupture directivity. When you start having multiple earthquakes in the same sequence, some of them will propagate from left to right, and some of them will propagate from right to left. And although the sense of slip is the same, but because of the direction of propagation, the tension and the compression quadrant will kind of switch here. So this is one way to see this, and it only emerges when you start having these different cycles. In these plots, which we're going to talk about a lot today, the horizontal axis here represents position along the fault, normalized by the nucleation length, and the vertical axis would just describe time steps, simulation time steps, and the contours that I will be showing later represent slip rate on the fault surface. And these kind of dots here represents where the rupture starts. So the different shades would represent different amplitude of slip rate as the rupture is propagated. So the first mechanism that contributes to accumulation of plasticity and damage on both sides of the fault is rupture directivity. The second one that's really important and usually overlooked in single dynamic rupture simulation, because we just forcefully initiate the rupture on a predetermined stress state, is this aseismic slip, either aseismic slip just from the creeping patches as well as the plasticity accumulated by the aseismic slip. People, or in general, we like to think about plasticity to be associated with the fast propagating rupture. But if you have a slowly propagating crack, but still can generate enough stress concentration, it would also kind of generate plasticity. And that's what happened when you start having creeping fronts propagating from the creeping patches into the locked patches. You start getting stress concentration that can accumulate plasticity. And in general, as the creep migrates through the locked patch, it also causes its own changes in the mean stress. So that's something we have to keep in mind, that a dynamic rupture in the sequence simulation, each one of them starts in a different stress state that depends on the history of the deformation. The third mechanism, which was really interesting as well, is that there's co-evolution of the mean stress and the plastic strain accumulation. You see here, for example, this is just an example of a dynamic rupture, a single dynamic rupture, just to illustrate the point. This dashed triangular fan-like is where the plastic strain is accumulated. But then I'm highlighting here in this dashed rectangle a region where you actually get, where plasticity is accumulated, you actually get increased compression after the plasticity has accumulated. So when the plasticity is accumulating on the tensile side, you get increased compressive perturbation, and that carries over to the next cycle. And this was highlighted in a previous study by Templeton and Rice. You could see that there's a residual stress perturbation in the extension pattern when you just have the plasticity accumulation. So plasticity, it changes the mean stress, and the mean stress in turn would change the strength which affects the plastic strain accumulation in subsequent ruptures. So all of these features can only be realized when you start looking at the sequence of earthquakes and aseismic slip, the interaction between aseismic slip and the stress state, interaction between plasticity and the stress state, and having the ability to generate a nuclear rupture at different places spontaneously. The other thing that we realized from this is that the strength of the fault zone actually altered the seismicity pattern. So if we ran, say, an elastic simulation with the same frictional properties and the same fault properties, we get the elastic reference here, which is kind of periodic, and fault spanning events. Now, if we added plasticity and we start reducing the strength of the bulk, it's still stronger than the fault, because the fact that the fault has existed is that it's weaker than the surrounding bulk. But if we start reducing the cohesion and start looking into weaker bulk, what you observe here is that you start transitioning from less complex behavior to more complex behavior. So for example, looking here, you get more or less patterns that are repeated, patches or cycles or groups of events that are repeating, and all of them is fault spanning events. Perhaps here's a doublet, small earthquake followed by a large earthquake, but there's more or less kind of repeats. Similar, but on the other end, when you really have a weak bulk, you start seeing a significant segmentation, spatial segmentation. So for example, here's a small event, here's another small event, and then a full spanning event. So you lose this characteristic earthquake cycle that you get in the elastic case. And this is actually associated with what we just mentioned related to partitioning of deformation. In a strong bulk, you get more localized deformation of the fault and less plasticity accumulating in the bulk. But in the weaker bulk, you get more distributed deformation. Yes?
Do you think of this in relative terms or in absolute terms? Like if you make the fault stronger for a constant fault strength, do you think you get similar behavior that is
I think it's
more heterogeneous behavior in places where the faults are comparable to the fault?
Yeah, this is a great question. I believe it's more related to the relative strength between the fault and the bulk. Because remember, both plasticity and friction are normally stress dependent, right? So it's how the relative properties are compared to each other. That's what's controlling. Yes.
In the beginning, you mentioned ergodicity. In this case, it always goes into the same pattern of the same behavior, no matter how you start it. It can run away into a condition where
if I look at say slightly different initial conditions, I will land in the attractor that's characteristic for the system parameter. Maybe the evolution will be slightly different, but each of these classes have their own attractor that is distinguishable from one another, but is insensitive of this initial.
right.
And this is just to highlight what I mentioned here. I could look at, say, the potency as a function of time, which is a measure of how much slip is localized on the fold. And I can come up with a similar quantity for integrating the plastic strain in the bulk. So I can get some sort of, and the integral of the plastic strain on the bulk that's comparable to the potency, which is basically the integral of the slip on the fold. And you could see that as you reduce the cohesion, these lines becomes more and more towards this one, right? So you throw in more and more deformation in the bulk. When it's weaker, it's more and more inelastic deformation that leads to more complexity. But I would like to highlight also that look at these different scale here. This is like 10 to the power -1, whereas this one is 10 to the power -3. So this big change in the qualitative behavior is not associated with significant kind of inelastic deformation in the bulk. It's still 1%, perhaps when we measure that. But it's because something that physicists also observe for self-organized system, when you introduce plasticity, you cap the ability of the fold to concentrate the stress. In an elastic system, the stress concentration increases as the rupture expands. But with this system that has a certain yield strength, you cap the stress, and hence the stress, if the fold tip eventually run out of the driving force, and that causes the rupture to self-arrest. So this is kind of a self-limiting process in some sense. So let me show you just a couple of videos to break the monotonicity of what I have presented here. The first one is a video that shows the co-seismic plasticity accumulation influenced by the residual stress field that is being perturbed because of the aseismic deformation and the prior history. In the top panel, that shows the slip rate on the fold, the central one, which shows the plastic strain accumulation, and the bottom one, it shows the mean stress as the aseismic creep penetrates through the fault and then the rupture starts. So let's see here. And this is based on the nucleation location and the sense of rupture, which is right lateral. We are expecting to have plasticity mainly accumulating on the tensile quadrant, but here's what happens. So we'll see as the aseismic creep is penetrating, the normal stress is changing, and then the plasticity is actually accumulating in the opposite direction of what we have expected. And the reason is this creep in front is carrying this tensile mean stress perturbation, making the system weaker in that side. So I will run it again. Here's dilatational quadrant, here's compressional one. But then even if the dynamic rupture is adding compression here at the bottom, but initially it encounters the tensile mean stress that was carried by the creep in front. So that's one important distinction that we have discovered. The other one is the coevolution of the plastic strain and near fault mean stress as well over cycles of earthquakes. So now I will run not only for a single rupture and the previous aseismic creep, but I will show you the evolution throughout the history. Again, this quadrant here, the slip rate, this one is the plastic strain accumulation, and this one at the end is the mean stress evolution. So now you would see that the slip rate here is changing over multiple scales, like you would see it changing from maybe 10 to the minus 10 to 1, and then going again. And you could look at the plastic strain, and you would see this kind of seismogenesis, because we are growing the fault zones as a function of the repeated earthquake that we are observing. And you could see bands and broadening of the plastic zone. And then also you see a very heterogeneous stress field that's emerging as this sequence goes on and on. And I'm just focusing here on a really narrow region near the fault. You would see also that the stress that as measured by the mean stress in the bulk has these alternating bands of dilatational and compressional quadrant.
So those oblique offshoots, do you think they eventually become fault
They could,
zones?
and if we allow them in the model to make faults, they can. Yes, exactly.
Right.
How does your model terminate at the bottom?
Turn what? Sorry.
Well, you have a fault, and
Yeah.
then it extends into the ductile zone.
Oh, okay. So these models, I should have been more careful here. These models are 2D plane strain models and are driven by creep on the edges, not at depth.
Mhm.
So you have a central velocity weakening patch, and then there are boundaries of velocity strengthening. And I imagine that the loading are coming on the edges of the fault. So it's not a three-dimensional system. So, but they are driven basically by this constant plate rate loading at the edges of the fault. Yes.
Is the loading at the boundary of the domain is uniform, right?
Yes, at the edges of the domain is uniform, but if this is large enough, then the fault would experience a uniform loading.
Yeah, if you have like a heterogeneous loading, will you expect a more like complex distribution?
It's possible, right? But even in this simple uniform loading, because of the feedback between the fault slip and fault plastic deformation, you start getting this complexity naturally. And then the last one that I wanted to show you is something interesting. When we zoom in on one of these events, we can start actually seeing some sort of intermittent propagation, irregular plasticity accumulation, and delayed nucleation patterns. So let me run this here. Plastic strain at the top, and the bottom is just the slip rate, and I will just run it fast here. We could see, for example, accumulation of some plasticity, and ahead of the rupture tip, because of the stress concentration and the irregular stress field, you could actually get not necessarily continuous plastic strain accumulation, but you could start accumulating plastic strain in patches which are weaker or having lower stress. So if I just zoom in here a little bit faster, you start seeing these kinds of jumping. The plasticity for some period of time pins the rupture, and the rupture starts to accumulate the stress behind the plastic zone. So the rupture tip eventually jump, and you start getting this kind of intermittent propagation. And eventually the rupture would be energetic enough to rupture through and continue propagating once it finds the right stress conditions. So this is a single event that tries to nucleate, and then it gets arrested, tries to nucleate again and gets arrested because of this accumulation of the plasticity in front of the rupture tip. And another thing that was really surprising for us, but again, of course, this is mainly because of the inelasticity of the bulk. If you ran a simulation in a linear elastic material on this strike slip fault, you would expect that the normal stress would not change on that fault. It's a nodal plane. And you would expect the fault just to rotate and not develop in undulations. But in this case, we actually observe two things. First, we observe this is the fault profile. So at the end of the simulation, you can actually look at how the initially straight planar fault ended up in terms of its deformation in the normal direction. So we see that it actually becomes kind of undulated. So there's some sort of roughness that emerges naturally from this. And moreover, this is a measure of the normal stress on the fault. And you could see that the normal stress itself becomes really heterogeneous here as well. So you get some strong fluctuation in the normal stress that will not be as present in the elastic simulation. And when we looked at some sort of comparisons with observation, although I would put a disclaimer here that our simulations are done under certain conditions, like you imagine taking a cross-section in the fault and run a plane strain simulation. These observations are primarily at surface, but there are similar principles, right? And one observation that emerges naturally is that the plastic strain, the equivalent plastic strain, decreases as a function of distance from the fault. So as you go further from the fault, the plastic strain decreases, and this is similar to what Heather and Emily have reported in some field observations in their collateral damage article. Another feature that emerges naturally as well is how the width of the damage zone increases as a function of the slip on the fault surface. And we observe that as the slip increases, the width of the damage zone increases, but it eventually saturates. And this is associated primarily to the ability, again, of the rupture to concentrate the stress away from it. And as you start accumulating this plasticity, you deprive the rupture from doing that. So if you are not adding much stress away from the fault, the damage zone will not expand. And this is, again, in line with these observations from Savage and Brodsky. But I'm saying in line, and I'm not trying to quantify this again because of the different conditions, but it seems like a generic observation. And then finally, I showed you these alternating bands of tensile and compressive mean stress perturbation that emerge as a function of the earthquake cycles. And it turns out that this paper, for example, Rosenthal GRL paper, they observed similar pattern from analog experiments. For example, near the edge of faults, when they tried to slip, they found alternating compaction and dilatation. In our case, it's just the normal stress perturbation, as well as from maybe geodetic data on the San Andreas fault.
But here that permanent deformation goes far out from the fault.
Yeah, so basically it will depend, all will depend about the scale, right? It's in here, maybe I haven't mentioned this, but there's a fundamental scale, this process zone that is controlling the width of these features. And if this becomes bigger, maybe near the surface it becomes bigger, then it's actually leading to more extensive deformation. So just in the last maybe 10 minutes, I will show you other things that this simulation framework can do, and addressing some of the questions that were coming up. So far I showed you just a single rupture. Here we are looking at fault step overs, and that's an important problem when you have a fault step over, which is basically two parallel faults or nearly parallel faults that are overlapping but separated. This is an important problem in seismic hazard because we are interested, for example, in the probability of jumping from one fault to another. And in that case, this framework can actually tell us how the interplay between the faults affect the evolution of seismicity, how the damage and plastic strain is evolving as a function of the earthquake cycle, and also how the direction of the stresses emerge. So I will just go briefly through these different cases. For example, here is just a snapshot extracted from a longer sequence. You could see that in this case, one fault would kind of rupture and then it arrests. And then it causes a stress perturbation that creates another rupture on the second fault. And then you get a more complex sequence of events on the second fault before the rupture kind of starts again on the other faults. So there's an important interaction that happens here between the two faults. The other thing that I wanted to highlight is we could start seeing emergence of features related to the fault zone. So again, if we are allowing faults to evolve, for example, in this case, we would observe kind of a horsetail deformation here and the emergence of wing cracks at this location, we get an intense kind of plastic strain accumulation and damage in the area, in the overlapping area of the two faults. And if I look at the mean stress, I actually find an increased magnitude of the mean stress in the overlapping region. And this can become clear here. When in this particular simulation, we started with a compression of 50 megapascal, but you could see that the principal stresses can reach minus 300. So as you go further and further in your sequence, you could actually start testing the limits of your constitutive relation. Remember, we used just Drucker-Prager, where the strength is linearly dependent on the mean stress. But once you start probing this high level of confinement, then it becomes questionable whether this linear dependence is applicable, or you need to switch to some sort of a CAB model or some sort of a damage rheology that allows for crushing of rocks to happen, for example. One thing I want to highlight here, these are plots of the direction of the maximum principal stress, and you see away from the overlapping region here, you get the principal stress consistent with the background tectonic stress field. So it's here with 45 degrees. But as you cross the fault boundary, you see that there's a very rapid rotation in the stress field. So again, this kind of geometric complexity can locally influence the stress orientation significantly. And if we are looking at, say, if there are faults inside and there's some sort of reactivation by fluid injection or whatever, this kind of rapid stress rotation is important to take into consideration, because locally the stress orientation can be very different from the background stress field. And then finally, I would like to throw in here some things that we are trying to understand as well, related to the effect of damage on the spectrum of slip. So we can get fast earthquakes, slow earthquake, and get repeaters. So this is just, and I will show the continuum counterpart, but we just wanted to start with a very simple model of a spring block model on a frictional, latent state frictional interface. And this spring here is governed by an elastoplastic relation. And one important quantity, as I was mentioning, is the yield strength of your constitutive relation of your rock, compared, for example, to some measure of fault strength. And the fault strength which shows here is the normal stress multiplied by the reference frictional parameter. And you can see on the vertical, this is a phase diagram, on the vertical axis, you get the yield strength. And I would like you to compare this yield strength with the fault strength here. And on the horizontal axis, you get what we call the normalized stiffness, which is the stiffness of the spring divided by the critical stiffness that's required to nucleate instabilities in elastic material. And you could think of this K over KC as a ratio between the length of your fault and the nucleation length scale. So here one means your fault is as big as the nucleation length scale in the elastic case. Greater than one means that you have a shorter fault, and larger than and smaller than one means you have a much bigger fault. So as you go in this direction, you imagine considering more compliant spring stiffness, which means you are considering larger and larger faults compared to the nucleation length scale. But what's particularly interesting here is that for some range of yield strength, like if your yield strength is low and approaching the fault strength, even if the friction is velocity weakening, you can actually get a locked behavior. So the fault will not move no matter what, because the deformation would just be primarily accommodated by the bulk, and the bulk will not allow the stress to concentrate on the fault to allow for the rupture. But then depending on the yield strength and this stiffness ratio, you then can get stick slip, slow slip, or stable creep. I'll just show you very briefly examples of this when we take this simple model prediction to the continuum level. for different types of magnitudes of yield strength, you get, for example, from locked region to some sort of aseismic transient that I will show you in the next slide. Some sort of what we observe would be similar to repeaters. And remember here, the fault doesn't have rheological heterogeneity, but it just naturally kind of regulate or control the extent of the rupture. So you get these kinds of events that may not be exactly small repeating earthquake, but have some kind of characteristic pattern here. They are emerging and are stopped by the accumulation of plasticity, not from the heterogeneous rheology. And then another case here, when you start having a higher yield strength, then you start generating more seismic events. But for example, in this case, they are all kind of segmented and partial ruptures. If I look at the seismicity pattern on the fault surface itself, that's another way to show them. The map peak slip rate is here. For the locked, you barely see anything. For the aseismic transient, interestingly, you see patches or swarms of these slow slip events where the amplitude maybe is like 5 times 10 to the minus 9. Some of them would actually grow to 10 to the minus 8. But those can actually be very well, perhaps in another model, explained by periodic fluid kind of pumpage, for example. And then these, what we call repeated, but they're not exactly repeated. You get closer to seismic instability, but kind of this more or less is close to being periodic, and then you get very complex pattern. And if I zoom in one of these swarms, in some sense, I can see that they extend over maybe, some of them can extend for a couple of years. Each one of these spikes can extend for maybe months. And then if I look at their stress drop, they're really very low stress drop events, maybe 0.05 to 0.1 megapascal. And similarly here for these kinds of, again, these are all still aseismic, you get some sort of more or less periodic pattern with a stress drop of 2 to 3 megapascal. We still try to quantify other statistics for these kinds of localized events. So in conclusion, I hope I have presented just a tool, like Phoebe is a tool to allow us to investigate fault behavior coupled with fault zones beyond elasticity. And so it's a tool that gives us a window to understand high resolution fault zone physics. Importantly, from our exploration so far, the partitioning of information between fault slip and off-fault bulk contributes to this emergence of seismic complexity. And very important, I think, from our perspective is that the width of the plastic zone and even the plastic strain accumulation is still small compared to the fault length as well as the potency of the event. But even if they are small, they still have significant impact on the rupture characteristics because of this feedback through the stress saturation. And then hopefully there is still plenty of room for exploration of fault zone to understand this highly nonlinear behavior of the near fault region and try to explore potential alternative hypotheses to what our observations are suggesting. So thank you very much, and I'm happy to take your questions.
Thank you. Thank you very much, Ahmed. We'll open it up for questions. We asked quite a few, but
Did you see any other Zoom people show?
nobody on Zoom right now, but please on Zoom, raise your hand if you would like to ask Michael.
The conclusion that there's a self-roughening process seems counterintuitive.
Yes.
I'm wondering if you could give me some way of explaining to my partner when I get home why.
It's an honor, but it was also surprising for us. But one way to think about it is that once you start accumulating this plastic strain in an asymmetrical way, then the two sides of the fault can be formed differently as the rupture is propagating. So perhaps what you would see is that the rupture tip would push a little bit more towards this edge, and then as it propagates further, it pushes a little bit more towards that edge. And these are inelastic deformations, so they locked in, right? And so this kind of self-roughening emerges naturally, and because of this asymmetry on the deformation. If it was elastic, linear elastic will not see that. But I will put a disclaimer here is that we are not yet solving this with finite deformation, in the sense that it would be really cool as the fault is self-roughening, then we can update the geometry and keep propagating this. But we haven't done that yet.
And I said it's counterintuitive because the whole purpose of sanding something, take something rough and make it smoother. Is it possible to do a stability analysis to show that variations grow, or is it too nonlinear to?
Well, I haven't tried it. It's usually, of course, very difficult once you have, like for these nonlinear systems, we try to linearize there. I could think about it. It's just, I think it's a bit daunting. Yeah. But this is an excellent question, and we were actually pretty confused and surprised by that.
Yeah.
As the accumulation of the plastic strain increase, is there a threshold? Like at this point, it will have like actually slip along this strain.
So anything here, you could always think about plastic strain. If you integrate the plastic strain in these two-dimensional models over the area, they give you some sort of a plastic displacement or slip, right?
Mm-hmm.
But the difference here is that they are not localizing into a single surface. So you could think about that more or less like a shear band, right? So the plastic strain that we are recording would definitely tell us that, well, this side of the shear band is moving against this side with that much. But we don't have currently in this model a mechanism, for example, that allows formation of localized surface, like along zero thickness interfaces like a fault. But the best, you could think of this as shear bands. So these are still localized deformation, but not on a zero thickness. They just have a finite thickness. And in reality, in fact, faults are not really sharp surfaces of discontinuity. They have some thickness, and we tend to think about the thickness of these faults as being maybe a multiple of grain size. So the short answer is yes, based on these localized bands, you could actually compute how much the two sides slipped past one another, but it's still a bit different from having a sharp edge. This or this. Okay.
I'm also wondering if there is a way to like actually compare how big or how significant this offered plasticity, offered deformation compared with the slip on the main fault.
Excellent. Yes. So we tried to do this by comparing this integration of the plastic strain in the bulk to the potency on the that's coming from. Yes, this one. For example, the vertical axis here represents the integration of the plastic strain over the area of the fault zone. The horizontal axis represents the integration of the slip over the fault length. So these two quantities have comparable dimensions. And you could see that on the vertical axis, maybe we have 2 orders of magnitude less than on the horizontal axis. So it's still small. And so you could think of this not because plasticity dissipates a lot of energy, but the more important effect, at least in our model, is that plasticity caps the stress. And when you cap the stress ahead of the rupture tip, you deprive the rupture tip from the ability to concentrate the stress further as it propagates further, and hence this acts as a self-arresting.
Great. Well, let's thank Ahmed again. Oh, great.
I'm looking this right. I wanted to ask if there's any way to force PB with a porphyric pressure time history, for example, as would be, for example, in a fluid injection setting or in a circulation zone.
Yes, we definitely can do this. We do have some work on injection-induced seismicity, but we are also very looking forward to extend this model to pore mechanics, right? So again, you could think of PB as just whatever you can do with finite element, you can still do with PB, and on top of that, you have the flexibility of what you can do with the boundary integral. So I think on our list, fluids are really important because when we talk about compaction and dilatation, this adds a very strong feedback into the fluid.
Awesome. So let's thank Ahmed again for conducting.
I believe we have refreshments in pizza. Thank you.